We continue in Chapter 7, looking at ways for estimating a different population parameter. We've already looked at how to estimate a population proportion in Section 7.1. Here in Section 7.2, we'll look at how to estimate a population mean. The main goal of this section is to present methods for using a sample mean, x bar, to make an inference about the value of the corresponding population mean, mu. Recall that x bar is a sample statistic because it is the mean of a sample of values, and mu is our unknown population parameter because it represents the mean of the entire population of interest, which we do not yet know. As in the previous section, we can start with a single value called the point estimate. The best point estimate for mu is x bar. So we say that x bar is the best point estimate and is the single best point value that will help us get a sense of the value of mu. We also talked about the fact that x bar is a good starting point for estimating mu, but that we really should stretch out a certain distance to the left and to the right of x bar to create a comfort zone known as a confidence interval. We'll see a lot of similarities in this section to Section 7.1. And we will not cover how to determine what sample size is needed going into a study because these methods require us to make some bold assumptions. Let's look at how to construct a confidence interval to estimate an unknown population mean. Let's review some of the labels that will appear in our calculations. Again, mu is the unknown population mean that we are trying to estimate. X bar is our known sample mean. It is the mean of the values that came from the sample drawn from the population. Lowercase s is the standard deviation of the sample values. N is our sample size, and capital E will once again stand for the margin of error, and that is the distance from our point estimate, which is the center of the confidence interval, out to each of the two limits, the lower limit and the upper limit for the interval. There are some requirements that must be met in order for us to construct a confidence interval meaningfully. First of all, our sample has to be a good sample, meaning that it is a simple random sample. In our very first module, we discussed how using a poor sampling technique could result in some data that just isn't very representative of the population from which it came. The second requirement is really the most important, and that is that the original population of values must be normally distributed, or if it is not, or we simply do not know if it's normally distributed, we must compensate by having a sample size that is larger than 30. If these are not met, one or the other, then the construction of the confidence interval will just not be meaningful. Here we see some similarities to our work in Section 7.1. You might recall that in Section 7.1 we were estimating a population proportion P, and so when we wrote our interval in a three-part inequality form, we said that P, our unknown population proportion, falls between P hat minus the margin of error and P hat plus the margin of error. Here we have different symbols because instead of working with proportions, we're working with a mean. So we're estimating mu, and we say that mu is somewhere between x bar minus the margin of error or x bar plus the margin of error. The margin of error is calculated differently than what we saw in Section 7.1. It is still the product of a critical value and a sample error. The critical value is a new type of critical value called a t-value instead of a z-score. We'll talk a little bit more about these t critical values in future slides. The sample error is equal to the sample standard deviation divided by the square root of the sample size. We will also see the appearance of a new notation, df, which stands for degrees of freedom. Degrees of freedom is simply our sample size minus 1. The confidence level Again, mirrors what we saw in section 7.1 and has the same interpretation. A confidence interval is constructed so that it is associated with a chosen confidence level, such as 0.95, which is our most common. We also saw 90% and 99% confidence levels, and these are also possibilities, as are really any other levels as well. 90%, 95%, and 99% are simply the most common, but we are not restricted to those three values. The critical value t is somewhat related to a z-score. However, there are an infinite number of t distributions because there is a different t distribution for each sample size. For example, there is a t distribution when our sample size is 10. There is a somewhat different t distribution if our sample size was, let's say, 15. Now, even though they are very similar, there are enough differences so that our answers will vary. There is a table that is available in your formula packet labeled Table A3 that shows a summary of some of these T critical values, and you can refer to Table A3 to find the critical values if you know the degrees of freedom, which again is the sample size minus 1, and you know the area in one or both tails. Again, using Table A3, you can find the critical value t that corresponds to a given sample size and to a chosen confidence level. It does require a little bit of work because recall that a confidence level is complementary to the area in the two tails. So for example, for 95% confidence, the area in the two tails must make up the other 5%, or 2.5% in each tail. That is something that you'll have to look up at the top part of Table A3. Now that you have chosen the correct column corresponding to the confidence level for your problem, you'll have to intersect it with the correct row that corresponds to the degrees of freedom, which is your sample size minus 1. Where the degrees of freedom and the area in one or both tails intersect, that point of intersection, in other words, inside the body of the table, is the critical value t. This differs from the z-score table where the table entries represented areas under the curve. In Table A3, the entries of the table do not represent areas and instead represent critical values. Here's a visual of what some of these t distributions look like. You see that they are symmetric and they are bell-shaped, just like the normal distributions were. However, the spread, or the standard deviation, is different than the normal distributions. But you see how similar they are in shape. However, the area under the curves will vary slightly over certain regions depending on the height of the curve. That means that you have to choose the correct t distribution carefully based on your sample size, which will determine the degrees of freedom, and the confidence level used for your confidence interval, which will determine which column of Table A3 to use. We're going to show you how to use your TI-84 calculators to construct these intervals, but it's a good idea for you to have a basic understanding of how to construct these intervals manually. Just as in section 7.1, we will need to calculate our point estimate, which in this case is our sample mean x bar. Then we will have to calculate our margin of error, which requires us to look up the critical value t and then multiply that by the sample standard deviation and then divide by the square root of the sample size. We have a problem in the book where we had a sample size of 6, which means that the degrees of freedom is 6 minus 1, or 5. For a 95% confidence level, we would have to look at Table A3 and find the column that corresponds to a total area in two tails equal to 0.05, which is the complement of 0.95, or we could look at the column that is labeled as having an area in each tail equal to 0.025. In fact, it'll be the very same column, just with two different labels above it. You'll see that the critical value for this situation is equal to 2.571, Again, that is the number that is in the body of the table where 5 degrees of freedom, the row, intersects with a column for the correct area in one or two tails. We can also use technology, although I don't prefer this, by using the inverse T command under the distribution menu of your calculator. If you want to practice, you'll go to second, vars, which will get you to the distribution menu, go to inverse T, and then you can write the area in the two tails and the sample size, which will then tell the calculator what the degrees of freedom are. Let's show you how to build a confidence interval to estimate a population mean using the sample data provided here in this example. Here we're looking at certain weights of Reese's Peanut Butter Cup miniatures. In fact, we have 6 values, and these values represent grams. Now, because we have the original values instead of summary statistics like X bar, we can go ahead and enter these values into our calculator and then use the appropriate command to build the interval. I'm going to go ahead and switch over to my calculator app to show you how to do this. You might want to write these down and follow the steps yourself so that you can practice. Okay, let's go to my calculator app. You'll see that prior to recording this video, I went ahead and entered those 6 values into the list editor. To get here, you'll go to Stat, Edit, and then enter the values into list 1. Once you have the values entered in your list, you're going to quit out of this screen and go back to the home screen. And now we're going to go to Stat, scroll to the right to find the Tests submenu, and then you're going to scroll down until you find the T-interval command. Once you choose the T-interval command, you will let the calculator know that you have data. In other words, you have the original values, and then where those values are stored. There will be some problems where you won't have the original data and you'll have some summary statistics provided to you instead. Those are problems where you have X bar and S provided to you, the sample mean and the sample standard deviation. If you have summary statistics, then you would scroll over to the stats command and enter those summary numbers. But for this problem, we do have the original data, so we'll stay here and say that the values are in list 1. Leave the frequency at 1, and let's construct a 95% confidence interval. When we go to calculate, your screen should show you the interval. My screen is acting a little weird because it's on my iPad, but there it is. The population mean for all Reese's Peanut Butter Cups miniatures is likely to fall somewhere between 8.590 grams and 9.021 grams. Just as before, we'll go out to 3 significant decimal places. So based on this sample of 6 Reese's Peanut Butter Cup miniatures, here is our confidence interval corresponding to 95% confidence. If we took repeated samples of size 6, we would expect that 95% of the corresponding confidence intervals would contain the true population mean.